I explain the first three methods: feed index, Gordon method, and constant proportional loss ratio. Now I'm going to explain the SCS method. SCS stands for Soil Conservation Service. And this is let me write Soil Conservation Service. And I just started. And it's also known as the curve number method. So this method is an empirical method which was developed in 1970s, in 1972 by the US Department of Agriculture, which is now the National Resources Conservation Service. And this empirical method was developed and applied to small and medium catchments. And so with a relatively small and medium drainage area, and is widely employed in engineering hydrology because it's quite simple and one can easily estimate the fraction of rainfall which infiltrates and the effective precipitation. So the most important part of this method is that it uses an integral representation of the rainfall process. So this means that we need to use the cumulative quantities. So using when we use the feed index method, the Horton method, or the constant proportional loss rate, we always refer to the Hayet graph. Now, when we have, so we start from the Hayet graph J, which is a length over time, and here we have our rainfall event. Well, if we assume that delta T is equal to 1, then this one also represents the precipitation depth. Okay? And this method is applied using the cumulative quantities. So this means that here we have time. Here we label P in capital letter as our cumulative precipitation. So we have this first precipitation depth, which is H1. Here we have our second precipitation depth, H2, and here H3. Cumulative means that at the first time step, 1, 2, 3, the cumulative precipitation is exactly equal to H1. So we simply report here H1. At the second time step, we need to sum up the first two bars because it's a cumulative approach, it's an integral representation. And so here we have this first bar. And from this value H1, we need to sum up the value H2. So this is H2, and this value here is H1 plus H2. H1 plus H2 plus H3. Okay, so please remember that this method uses cumulative quantities. So we should always refer to this representation. So it's an integral representation of the rainfall process. So the variables used in the SCS method are 4 and are. The first one is P, is always measured in millimeters. Okay, so if you have value in centimeters, you need to shift in millimeters. And this is the total rainfall. So it's important to use this unit of measurement because then later you will see that this method is based on a relation which is based on this unit of measurement. Okay. Then we have the second variable is IA, expressed again as millimeter, which is the initial abstraction. Then we have FA, which is the actual cumulative infiltration. And we have the PE. So again, FA is expressed in millimeters, and PE, whose units are again millimeters, is the effective, the rainfall excess. So I report here the hydrograph, G, and the B. So we have 1, 2, 3. So the SCS method is based on these assumptions. So we define the initial abstraction. This is a quantity, a water quantity, that infiltrates at the beginning of the rainfall event into the soil. And this quantity does not contribute to runoff. So is a rainfall quantity, so a water quantity which is subtracted from the total incoming rainfall and does not contribute to the surface runoff. So basically, we may say that we have the that P, which is the total rainfall initial rainfall excess. So this means that potentially the difference between the total rainfall minus the initial abstraction, so the initial abstraction is the water that fills the ponds, the puddles in the soil, okay, on the surface. So maybe we can identify here this IA as, let's say that this is my IA. It's a volume, so it's this integral, this area here, that does not contribute to the runoff. So let's say that maybe we can recall to the storage threshold model. It's somehow a Dunnian approach. So the first fraction of rainfall does not contribute to runoff. And this is IA. So here we define P minus IA, which is the potential rainfall excess, whereas this PE represents the actual rainfall excess. So maybe I just add here this adjective. And so here from this cumulative plot we have that this IA is a value here. And so this value, so this is subtracted from this P. Okay, here, so in the cumulative plot, we are not looking at the area below the curve, but at the value we read on the vertical axis. Okay? So this is a fraction which does not contribute to runoff. So it infiltrates and is excluded from runoff. Then the rainfall event continues, and so we may apply this Boltonian approach, and we have that a fraction of this part infiltrates, and the fraction contributes to the runoff. So basically it goes like this. So here we identify FA, so the area below this curve is the fraction which infiltrates, whereas this part is the PE, the rainfall excess, the actual rainfall excess. So this fraction, this additional fraction of rainfall which infiltrates into the soil, which is the actual cumulative infiltration, is an additional contribution to IA. So we have this fraction infiltrates, and then also FA infiltrates. And the SCS method is based on the assumption that FA is smaller or equal than S, where this S is the potential maximum retention is always measured in millimeters. So it's the potential maximum volume that can be filled in by water. So it's the void volume in the soil. So the maximum water, so the maximum storage of water that can be potentially filled in. everything is clear? So we have the total rainfall. At the beginning of the rainfall, we have a fraction which does not contribute to runoff, so it immediately infiltrates. And this is IA. So P minus IA is the potential rainfall excess. So potentially, I have this rainfall excess which may contribute to runoff. But actually, what happens is that only a part of this P minus IA, so only a part of this contributes to the rainfall excess. So and here we have, let's say that this is PE and this is FA. Okay. So this method is based on the assumption that the ratio between actual and potential quantities, so the potential so the actual rainfall excess divided by the potential rainfall excess equals the actual cumulative infiltration divided by the potential maximum retention volume. So this means that the actual rainfall excess is PE divided by the potential rainfall excess, which is P minus IA, should be equal to the actual cumulative infiltration, which is FA, divided by the potential maximum retention, S. So I label this equation as equation 1. Then we know also that the precipitation, the cumulative precipitation, is given by the sum of the initial abstraction IA plus the cumulative, the actual cumulative infiltration plus the rainfall excess. So P is IA plus FA plus PE. And this is equation 2. So our goal is to determine PE. So each value of this equation. So we know P, we want to know IA, we want to know FA and PE. So the rainfall excess which contributes to the runoff. So to do this, we need to solve this equation and we express FA as a function of this. So basically, FA is P minus IA minus PE. This is 3. And so here we substitute 3 in 1 and we solve So we have that PE divided by P minus IA is equal to, and I use the equation 3, P minus IA minus FA, minus PE, sorry, divided by S. So we have PE times S is equal to P squared minus P IA minus P times PE minus P IA plus IA squared plus PE times IA. So we move to the left hand side, the terms with PE. So we have that PE times S minus IA plus P is equal to P squared, and here we have minus PIA minus PIA, so minus 2PIA plus IA squared, which is exactly the power 2 of P minus IA. Okay. Here. So now we have that PE is equal to P minus IA to the power 2 divided by P minus IA plus S. And this is the rainfall excess. So to quantify this, we need to know the amount of the initial abstraction, the value of IA. And if we assume, so from empirical studies, which were carried out in small and medium-sized catchment, the people who developed this method, so the US and Department of Agriculture, discovered that IA is equal to 0.2 times S. So it's a fraction of the potential maximum retention storage. Is always expressed in meters, and this applies under normal antecedent soil moisture conditions. So in the majority of cases we have that IA is equal to 0.2 times S. So we have that normal antecedent soil moisture. So in this equation we know P. We, let's say, somehow know IA, but we need to estimate IA, we need to define S. Okay? And S is the maximum potential retention on the physical characteristics of the soil and of the watershed, and S is expressed as a function of the curve number, which is a dimensional number expressed as a function of the land use and the soil moisture condition. And S is expressed as 25,400 divided by Cm minus 254, and is always expressed in millimeters. This Cm, this curve number, assumes values between 0 and 100. So Cm is between 0 and 100. And we have that Cm is equal to 100 when we have water surfaces and impervious surfaces, so completely impermeable surfaces. So Cm is equal to 100 for impervious. Whereas for natural soils, we have that Cm is smaller than 100. Remember that Cm has no dimensions, so it's adimensional. So, usually the Cm is, they provide tables, and in the handout Professor Montanari uploaded on the web, you may find a part of the table produced by the US Department of Agriculture, where the curve number is expressed as a function of the land use. So we have values for cultivated land, for commercial and business areas, for paved parking lots. So we have different types of soil use. And also we have different values for which distinguish among different hydrologic soil type. So more permeable and less permeable soil type. Okay, but then you may find this table, so it's only for your information. So basically, you know the characteristics of watershed, so you can estimate the value of the curve number. From the value of the curve number, you can estimate the maximum retention volume, the potential retention volume. Okay? Then from S, you can estimate the normal, the initial abstraction FA. From this, so you know S and IA, you substitute it in this equation. You already know P because P is the rainfall event which is given, and you can estimate PE. And then finally, FA is P minus IA minus PE. Okay? So basically, this is the theory. And I prepared a quick exercise on the SCS method. So you can have an idea. So we just perform an application to a catchment with numbers, and also in the handout with this exercise with the final solution. So just to do a quick overview of what I explained. So we started from the infiltration models. We have three classes of models. Physically based models, so it's the Richards equation, which describe the physical mechanisms. Then we have the approximate models, which are an approximation of the physical process, and we have the greenhouse model. Then I explain the empirical conceptual models, which are based on two approaches, so the storage threshold and the infiltration threshold approach. And in this second group, I presented the phi index, so we have constant infiltration rate. Then the Orton method, so an infiltration rate which decreases in time. Then presented the constant proportional loss rate, so we have a percentage of rainfall which infiltrates and varies in time, and this. Okay, so I clean the blackboard. Do you have questions? Everything clear? Okay. Maybe I keep the equations. So we need PE then we need FA, which is B minus IA minus PE. Then we need IA, which is 0.2 times S, and S, which is 25420 divided by Cn minus 2. Okay. So the exercise is that we have, so given the following rainfall pattern and catchment properties, model the infiltration process and calculate the rainfall excess by lithograph. Okay, with the SCS method. So the rainfall pattern is this one. We have 3 hours event. This is our J. And in the first hour, we have a rainfall intensity. So here, and here. And we have that at time. So maybe I prepare. Time and hour, and this is J expressed in millimeters per hour. During the first hour, we have 50.8 millimeter. During the second hour, we have 76.2 millimeter, and during the third hour, we have 95 times 0.4. So this is the rainfall pattern, and basically this is the rainfall intensity, but also is equal to the rainfall depth, because we have that delta T is equal to 1. Okay, so maybe it's also equal to H, which is J times delta T, where delta T is 1 hour. Okay. Then we need to know the catchment properties. And so the watershed has a 40% of its area which is residential. A 25% which is open space. 20% is commercial, and the remaining 15% is industrial. Then, as I already said before, we have these different soil groups as a function of the permeability of the soil. So we have 4 groups, A, B, C, D, and I assume that here we have soil group C, D, C, and D. So basically from this information Then you go inside this table. So you have the soil, the hydrological soil group, and the land use description, and you read the curve number. So we have that in this case. So the first curve number is 83, so curve number. The second is 80, 94, and 93. So we need to know the average curve number within our watershed. So our average curve number is basically 0.4 times 82, 83 plus. So each percentage is multiplied by the curve number value to have an average. Plus 0.25 times 80 plus 0.2 times 94 plus 0.15 times 93. And our average curve number is equal to 86. And the curve number has no dimensions